Right.
Should we set the camera in my house so that people stop coming in right away?
So so today we're going to finish up talking about ANOVA. We're going to talk about Latin squares, and we're going to talk about missing cells. If you're watching this on YouTube, there's two separate videos. If you're listening there, it's all together. If you're in the room, you're wondering why I'm not talking to you. So let's talk about Latin squares. Also, let's get this. There it is. Okay, good. We've discussed procedures for dealing with nuisance variables, right? Those are those extra variables. They have extra variance, but that's a problem, but we can account for it. Like blocking, right? Remember the example of people's previous experience learning another language? We thought that would be an important thing in language learning, so we block on that variable. Same thing with repeated measures, which are just a special case of blocking. If I test Victoria over and over again on something, and then I also test Chloe over and over again on something, I can put the fact that they're the same people being tested over and over again into the model and take out some variance. It's really just blocking, but the block is a single person. There's also a way to do this statistically. And I am going to talk about this in incredibly broad strokes. Okay? But there's something called ANCOVA. It's analysis of covariance. So what it does is it finds a covariate. So let's say we're looking at income and education are a couple of our variables, and we know that income and education correlate. They just do. You have to like it. It's the way it works. So if that's the case, maybe we want to factor what's called factoring something out. So it's like we can't control for it through blocking or repeated measures. What we do is we're going to control it through an ANCOVA, through a covariate. So we say, how much does education covary? How much does it overlap with income? And then that variance we remove from the model, and then we do the analysis. It is a lot more complicated than that, but that's really all you have to know about how ANCOVA works. If you ever want to do an ANCOVA, have fun. But it's not the best approach to me, because it'd be better to deal with these things through design, if we can, but sometimes you can't, so you use a covariate. And that's all I'm going to say about ANCOVA. That was an odd noise. Okay. What was that? I don't know. Doesn't matter. So what if you have two nuisance variables? Oh God, they're drilling holes again. Does everybody hate me or something? Don't answer that. Yeah, because I'm afraid you might say yes. So what if you have two nuisance variables? So now what you have is you have two nuisance variables and, of course, a third variable, the way you're interested in your dependent variable. This could happen, and it does, and it's rare. Okay. You can't put them together. I put an example up on the LMS about how to do this with SPSS, and it'll show you also just an example. I think I lifted the example out of the book. So what we're going to do is we're going to put, I don't know why I'm so excited. There's no need for that many exclamation points. Or any, really. That's not that exciting. I'm, it's getting to the end of the term, and I'm excited about not doing this for a while. So you put one nuisance variable in a row and one in a column. So this is a useful kind of design, and you use it under very specific circumstances. Okay. Okay. So I'm going to show you what it looks like, and then we'll go from there. So what you do is you get something that looks like this. Now, up until now, A, B, C, and D have been the names of factors, the names of variables. They aren't here. This is, don't blame me, this is how people do this. I don't like it either. But the A, B, C, and D are different levels of a variable. And then we have two nuisance variables, 1, 2, 3, and 4 on, put that over there. So A, B, C, and D, again, are levels of a factor. They are not independent variables. They are levels. I know it's annoying. I don't like it either. I wish to hell the world would decide to stick with notation and just use it. It's not how the world works, unfortunately. Come the revolution, it will happen. So a friend of mine used to say, come the revolution would say that, and then we talked about how we were both philosopher kings of the world. The world would be a lot better, I'm just saying. You'd all have all kinds of liberty. It would be great. Anyway, so each level occurs in each ordinal position. You see that? So A occurs in position 1, in position 2, in position 3, in position 4. B occurs in position 1, 2, 3, 4, etc. And each row and each column has each level once. So if we have an experiment like this, we have two nuisance variables and an independent variable that has 4 levels. So if we did this across everything, did it as a factorial, instead of, because what you have is one person, one subject in each of these cells, just one. But if we were doing this as a regular ANOVA, this would be a 4 by 4 by 4. So we'd have 64 groups. You can see why it's like, oh, I can't do that. We can't get that many people. There's too many. So I had a student years ago, this would have been 2007 maybe, 8, who used the Latin square for her honors thesis. And she was looking at it was odor detection. And hers, and I can't remember what the nuisance variables were, frankly, but they were different odors and could people detect them. And it was an 8 by 8 Latin square. So she needed only what? So what's 8 by 8? That's still 64 people. Had she done a regular factorial design, it would have been 8 by 8 by 8, which is what? That's 64 times 8. 464 times 8, 64, 128. 512. Yeah, that's a lot. That's 512 groups. So instead of that, she had 64 people. So there are times when you would do this. It's very rare, because it's rare when you're going to have 2 nuisance variables that are easy to measure, and it's rare when you're going to have the same number of levels of those nuisance variables as you have of levels of your independent variable. These are very specific designs. You'll likely never run into one. Like I said, my whole career, I have supervised 119 honors theses in my life. I've had one person use a Latin square. One. Jen Sushro. She's awesome. At least she was then. Perhaps she's horrible now. And when I said that, that's a horrible thing to say. Sometimes I run into her in the grocery store. Anyway. Like I said, you need equal numbers of rows, of columns, and levels of the independent variable. That's a hell of a restriction. So the model's weird. It's weird. Well, it's weird in a way, because it says that any score, so it's x equals mu plus alpha beta plus gamma plus epsilon, equals the grand mean plus the effect of rows, columns, and the independent variable. Oh, and there's error, of course. Typically, we don't call it error with Latin squares for some reason. We tend to call it residual. It means the same thing. So the variable we care about here is gamma. It's not alpha and beta. Alpha and beta are nuisance variables. They are things that we can measure and remove. Like how I'd like to remove the sound of that drill. So remember, these 2 nuisance variables, A and B, alpha and beta, rows, columns, are things you can measure that would affect the outcome, but you're not interested in. So again, thinking back to our blocking example, remember it was experience with another language. We thought that would play a role. Here we just have 2 of those kind of variables. 2 nuisance variables, not just 1. Okay, so what's the design look, or so the source variation degrees of freedom table looks like this. Rows, columns, independent variable, residual. P is the number of rows, it's also the number of columns, it's also the number of levels of the independent variable. So if you have a 4 by 4 Latin square, P is 4. If you have a 3 by 3 Latin square, P is 2, etc., etc., etc. And then you get p minus 1 for all rows, columns, and independent variable. And for residuals, p minus 1 times p minus 2. So p is the number of rows, columns, and levels of the independent variable. Remember, those all have to be equal, obviously. So if I give you one of these, so again, I just said, on the final, you're going to have, here's the source of various degrees of freedom table. Tell me what the design is. If you see rows and columns, you go, okay, that's a Latin square. I have to look for anything else. I know this is a Latin square. It'll never say rows and columns any other time. So this is sort of separate from the Yates stuff. Because if you see rows and columns, like, oh, that's all bets are off. I know what this is. There are p minus 1 degrees of freedom. It says we have 3 degrees of freedom for rows, columns, independent variable. Oh, it's a 4 by 4 Latin square. You just draw one. Straight up, easy work. You wouldn't be, I mean, I would be, if I were you, I wouldn't be surprised at all if this showed up on your final quiz. So when you see rows and columns and independent variables, you say, oh, that's got to be a Latin square. Got to be a Latin square. You notice anything there? There's something missing, right? There's no interactions. None. And how could you know there was an interaction? You can't. You can't because there's only one subject in each group. In each cell, there's only one subject. So you could never detect an interaction, even if it's there. So that means interaction would go to residual, would go to error, and again, making error big is bad. So you want to make sure there's no interaction. But how can you know there's no interaction? Because there's no way of measuring it. By being smart. Like you got to just do it by looking at old research and looking at sort of theoretical ideas and say, okay, do these variables interact? Because if they do, it could cause a problem. The nice thing is if they do interact, it's going to make you not find something. It's not going to give you false positives, but you might get a false negative, and you want to find things. You want to find things because you want to get publications, so you can get an NSERC, and then you get a postdoc, and then you get a tenure track job, and then you get tenure, and then you get promoted, and then it's great. I skipped a lot of stuff that's really complicated and hard, just let you know. I'm getting harder. All right. So conclusions about Latin squares. They're useful if you can meet their incredibly stringent assumptions. They're basically, you should probably avoid them because the assumptions are so stringent, but sometimes, like I said, one time in my career, it's been useful. Make sure there's no interactions, and again, you can't know that by looking at your data. You can only know that by looking at previous research. And again, you have to have equal number of levels of rows, columns, and independent variables. You can't have like a 3 by 2. There's no such thing as a Latin rectangle. You can, but it's really bad and don't do it. You can, but it shows up in graduate school as a what would you do in this situation thing on a stats test. It's something no one ever does. You can also do a Latin, you can do a cube. It's called a hyperlatin square. These start to get ridiculous because statisticians go, what if we made a cube? So then you get rows, columns, levels, independent variable, but also coming out this way. So you use I think you use Greek letters coming up this way. And then you could actually do different squares. So you could have one square, another square. That way you use Hebrew letters. It's all very complicated. No one does that stuff. It's all just the statistics journals. Or again, you go to graduate school, it shows up on a test as out. Oh, here's a couple of marks to see if you've been paying attention. That kind of thing. Don't worry. Regular Latin squares are fine. They're fine. I'd avoid them because they're complicated for most people, but they're actually a perfectly reasonable kind of way to do data analysis. Okay. All right. So that's Latin square. Any questions on Latin squares before we move on to talk about empty cells? Okay. So we'll stop this one.